Hey guys, welcome back to Domestic Tech. In this video, we are going to discuss the bitwise operators in C programming language. So sit back and let's roll on. A byte consists of 8 smaller units called bits, and a bit can assume either of two values, 1 or 0. This is the list of operators we can use to manipulate bits. Bitwise AND, bitwise inclusive OR, bitwise exclusive OR, NOT operator or ones complement, left shift, and right shift. All the operators listed in this table, with the exception of the ones complement operator, are binary operators, and as such take two operands. Bit operation can be performed on any type of integer value in C, be it int, short, long, and signed or unsigned, and on characters, but cannot be performed on a floating point values. In this video, I assume you understand how to convert a number to its binary form. Let's discuss AND operator. When two values are ANDed in C, the binary representations of the values are compared bit by bit. Result of AND is 1 only when both bits are 1. Anything else produces a 0. This table, called a truth table, shows the result of A ANDed with B for all possible values of A and B. When A is 0 and B is 0, A and B is 0. When A is 0 and B is 1, A and B is 0. When A is 1 and B is 0, A and B is 0. When A is 1 and B is 1, A and B is 1. So for example, if A and B are defined as integer, and A is set equal to 12 and B is set equal to 7, then A and B equal to C assigned 4 to C. AND operator take 2 bits at a time and perform AND operations on them. 0 and 1 is 0. 0 and 1 is 0. 1 and 1 is 1. 1 and 0 is 0. Note that integer is of 4 bytes, so it consists of 32 bits, but for simplicity we are just comparing 8 bits. Make sure that you don't get these two operators confused. The logical AND operator AND is used in logical expression for producing a true or false result. It does not perform a bitwise AND. Let's discuss OR operators. When two values are bitwise inclusive ORed in C, the binary representations of the two values are once again compared bit by bit. The result OR is 0 only when both are 0. This is the truth table for inclusive OR operator. When A is 0 and B is 0, A or B is 0. When A is 0 and B is 1, A or B is 1. When A is 1 and B is 0, A or B is 1. When A is 1 and B is 1, A or B is 1. So, if A is an unsigned int equal to 12 and B is an unsigned int equal to 7, then a bitwise inclusive OR of A and B produces a result of 15. 0 or 1 is 1. 0 or 1 is 1. 1 or 1 is 1. 1 or 0 is 1, which is equivalent to 15. Be sure not to confuse the operations of bitwise OR with that of logical OR. Logical OR operator determines if either of two logical values is true. Now, let's discuss XOR operator. The bitwise exclusive OR operator, which is often called XOR operator. The result of this bitwise operator is 1 when either A or B is 1. The truth table for this operation is shown here. When A is 0 and B is 0, A XOR B is 0. When A is 0 and B is 1, A XOR B is 1. When A is 1 and B is 0, A XOR B is 1. When A and B is 1, A XOR B is 0. If A and B were set to equal to 12 and 7 respectively, then the result of A exclusive OR with B would be 11, as illustrated here. 0 XOR 1 is 1, 0 XOR 1 is 1, 1 XOR 1 is 0, 1 XOR 0 is 1. This is the result of the XOR operations between A and B, and it's equivalent to 11. Now, let's move to NOT operator. The ones complement operator is a unary operator, means it operates on a single value, and its effect is to simply flip the bits of its operand. Each bit of the operand that is A1 is changed to 0, and each bit that is 0 is changed to 1. When A is 0, A complement is 1, and when A is 1, A complement is 0. It's simply flipped. If A is short int that is of 16 bits long and is set to equal to 43, then taking one's complement of this value produces a result of 20. Not 1 is 0, not 1 is 0, not 0 is 1, not 1 is 0, not 0 is 1, not 1 is 0. And we stop at last position of 1. This result is evaluated to 20. Now let's discuss a left shift operator. When a left shift operation is performed on the value, the bit contained in the value is literally shifted to the left. The operand on the left of the left shift operator is the value to be shifted, whereas the operand on the right is the value of bit positions by which the value is to be shifted. Bits that are shifted out through the higher order bits of the data item are lost, and a 0 is always shifted in through the low order bit of the value. So if A is equal to 3, then the expression A B equal to A left shift by 1 will result in 3 being shifted in one place to the left, which results in 6 being assigned to B. If you shift A one place to the left, you end up with 6. This is visual explanation of left shift. The last 0 right here is shifted out. The next 0 is shifted in, which will be the last 0. Then the one right here shifted as follow. The next 0 is shifted in, the next 0 is shifted in, the 1 shifted in, the 1 also shifted in, the last 0 shifted in, which will produce a space for another 0 to be shifted in through the low order, which will be equivalent to this. All these values, all these bits are shifted in one places to the left. This is explanation of left shift operation. This particular 0 is shifted out, then all other bits shifted in one position towards the left hand side and producing a trailing space which is filled by another 0. The result is evaluated to 6. If you shift A in 2 places to the left, the last 20 is shifted out, then all other bits are shifted towards the left hand side in 2 positions, and the trailing spaces is filled in by 2 zeros. The result is evaluated to 12. Another way to calculate left shift is by multiplying by 2 raised to power of right operand. A left shift 1 is equivalent to A multiplied by 2 raised to power of the right operand, which is 1. A left shift 2 is equivalent to A multiplied by 2 raised to power of 2, which is right operand, and it's equal to 12. Now let's move to the last operator. When a right shift operation is performed on a value, the bits contained in the value are literally shifted to the right. Associated with this operation is the number of places that the value is to be shifted. Bits that are shifted out through the low order bits of the data item are lost, and 0 are always shifted in through the high order bits of the value. Left operand is the one shifting, while the right operand decides the number of the place to shift. So if A is equal to 20, then expression B equal to A right shift 1 result in 20 being shifted in one place to the right, which results in 10 being assigned to B. This is visual explanation of right shifting operation. The last 0 on the right hand side is shifted out, and all other bits are shifted in one position, leaving a one trailing space which is filled with 0. The last 0 is shifted out, all other bits are shifted toward the right hand side in one position, and the last position is filled with 0, which is evaluated to 10. The A, while is 20 in this case, will be shifted by 2 places toward the right hand side. Just like left shift, it will result to 5. Another way to calculate right shift is by dividing by 2 raised to power of right operand. A right shift 1 is equivalent to 20, which is A divided by 2 raised to power of 1, and A right shift 2 is equivalent to 20 divided by 2 raised to power of 2, which is right operand. Points to take note. It should be noted that the C programming language does not produce a defined result. If an attempt is made to shift a value to the left or right by an amount that is greater or equal to the number of bits in the size of the data item. So on a machine that represents integers in 32 bits, for example, shifting an integer to the left or right by 32 or more bits is not guaranteed to produce a defined result in your program. You should also note that if you shift a value by a negative amount, the result is also undefined. With this, I hope you understand basic bitwise operations in C programming language. Thanks for watching. See you in the next video.